For the brain, we made an state machine with the states that starts with find landmark, that it moves around to identify an object that needs to be moved. And it goes then to wander to identify the rook ID. And after wander, once it identified it, it goes to target, which moves towards a convergence point, and it uses book 2. We also use the handle object to lift the object and then to drop the object whenever it's needed. And we also have the stop state to finish the process when everything is done. For the common filter, we first need to initialize our state statement with the current position and angle of the robot. Assuming that the sensor noise is represented in a Gaussian function, we do a Jacobian linearization based on the Taylor series expansion. Then as a result, we get linearized model of the robot's kinematics and its covariance matrix of odometry. We then compare the predicted positions with observed landmark position to compute the differences and estimate the measurements. We then define the measurement noise matrix, and for the Kalman gain, we calculate it to get optimally combine the predicted state with the actual measurements. We getting this data, we then publish it to obtain our sensor fusion-based robot.
For navigation algorithm, we implemented a book 2 because it can reach a global goal while only having local knowledge of its environment. First, it starts by turning around to look towards the goal. Then it starts to follow the imaginary line formed in between itself and the goal and the desired goal. Follow it until it reaches it and ending the program, or until it finds a wall in the middle. It will follow the contour of the obstacle until it reaches again the goal line, and then it repeats the process until it finds another obstacle or the goal is reached.
Then moving forward to the rock identification process, this flowchart synthesizes all the information regarding this task. First, with the initialization of our node, which then subscribes to the corresponding topics of the raw image retrieval and the camera information regarding the camera parameters, which are essential for the 3D position estimation of the Aruco markers. Then, whenever we receive a raw image message, it is transferred, converted from a raw message to OpenCV to be able to use a specific function which automatically detects the Aruco markers. Once a marker is detected, it then identifies the corner of the face of the cube and then calculates the 3D coordinates of the markers regarding the intrinsic parameters previously stored from the topic, and then we compute a function to estimate the 3D position of the marker regarding the position of the puzzle, to then publish this point as a set point or target point to be able to follow in order to handle the palette.
For the object manipulation, we first need to identify the Aruco markers using computer vision and the Aruco library. We then align the robot to the Arucos on the palette to precisely lift the object, and once it is aligned, we move forward and lift the palette with our own designed lifter. The challenges during the development were that we couldn't align the lifter with the palette, so we placed Minaruko in the palette. So we used visual servoing for the robot alignment. We had defective hardware, so we got new motors from Mr. Munoz, and for the wheels, and we changed the motors of our old motors to the new ones. And we had problems with the common filter implementation, but we gave small values to our noise matrix because the Aruco identification had little to no error in the measurements.